Good day and welcome to our class for today. In today's class, we are going to be proving, we are going to be looking at case 3, which is nothing but simply supported beam carrying a concentrated load not at midspan. So the beam we have here on the board is carrying a concentrated load that is not at the midspan. So we are going to be considering this case for today. So as always, I'll be drawing the shear force and bending moment diagram here, and the calculation will be in these two other places. So the first thing we are going to be doing is that we are going to be considering all the forces on this beam. So we know that upward force, the sum of upward force is equal to what? Is equal to the sum of downward force. This implies that we are going to be having RA plus RB to be equals to what? To be equals to W. So this is what we have. So this is let this be our equation 1. So next we are going to be taking our moment from point A. If we take moment about point A, summation of moment about point A is equals to 0. We are going to be having what is going to be nothing but what? RB multiplied by L, which is the total length, multiplied by L, which is total length, minus what? Minus W multiplied by A. So in this case, we are going to be considering all upward force as positive and all downward force as negative. Now, of course, we know that moment is nothing but what? Force times perpendicular distance. So we are taking moment about this point. So we have RB, which is positive, multiplied by the total length, which is L, and then minus W multiplied by its length, which is what? Which is A. So this will be nothing but what? RB multiplied by L minus what? Minus W multiplied by A. Everything equals to what? Equals to 0. This is nothing but what? RB multiplied by L minus what? W. If you take minus WA to the other side, we have what? We will have WA. So this is what we have. So let's make RB the subject. If we make RB the subject, what will happen? RB will be equals to WA all over what? All over L. So this is our value for RB, and we know that our RA plus RB is equals to what? Is equal to W. So we can find our value for RA here. If we substitute RB here, from 1, RA plus what? WA all over L will be equals to what? Will be equals to W. So this is what we have. So let's make RA the subject. If we make RA the subject there, we are going to be left with what? We are going to have RA to be equal to what? W minus WA all over what? All over L. So from here, what can we do next? We take the LCM. We have L multiplied by W is WL. This is what we have. L multiplied by W is WL. L divided by L is 1. Multiplied by WA, we have minus WA. So this is what we have. Now, of course, you can see that L is W is common here. So this will be equals to what? W into, if you factor it out, we'll be left with what? L minus A all over what? All over L. Now, if you look at what we have here critically, the total length of this beam is nothing but L, and from here to here, we know it to be A. So if we subtract A from L, we'll be left with what? B. So L minus A is nothing but B. So if we replace that here, this equals to W B all over what? All over L. So our RA is equals to what? W B all over what? All over L. So this is our value for RA and our value for RB. So RA will be equals to W B all over what? L, and RB is nothing but what? RB is nothing but WA all over L. So this is what? RB WA all over L. So that's that for our value for RA and RB. I hope you get that. So next we are going to be looking for what? Our shear force and our bending moment. So let's do that. So shear force So we are going to be doing our shear force calculation. Now, of course, we are starting from point B. Now, the shear force at point B will be nothing but what? Will be nothing but WA over L, because the shear force at point B is nothing but what? The reaction at point B. So our shear force at B will be equals to what? WA all over L. Now, for our point C, let's call this point C, where this load is directly on. Let's call this point C. Now, to get the shear force at point C, it will be nothing but what? WA all over L minus what? Minus W. That's what we have. So, also in this case, we are going to be considering upward force to be positive, upward force as positive, downward force negative. So if you are considering that, we are going to be having what? WA all over L minus what? W, to get the shear force at point C. So shear force at C will be equals to WA all over what? All over L minus what? Minus W. So this is what we have as our shear force at point C. So of course, can we take the LCM? Let's take the LCM and see what we get. So this will be equals to L all over what? All over WA minus what? Minus WL. So this is what we have. So let's factor out W. So if we take out W, this will be equals to W into what? This will be equals to W into A minus what? Minus L all over what? All over L. Now if we put a minus outside this W, if we bring out this minus outside this W, we have what? We have L minus what? A. So that if you multiply through, you get what we have here back. So our shear force at C will be equals to what? Minus W into what? L minus A. So minus W multiplied by L is nothing but what? Minus WL, and minus W multiplied by minus A is plus WA. So this will be all over what? All over L. Now, like we did before, we have already established that what? L minus A will give us nothing but B. So we will replace L minus A with B. So this will be equal to what? This will be equal to minus W into B. Or we can just say minus WB. So this is what we have all over what? L. So this is our value for what? For the shear force at C. So next, we are going to be looking for what? The shear force at A. Our shear force at A will be equals to what? So we have it will be equals to, don't forget, we are still considering upward force to be positive and downward force to be negative. So we have WA all over L minus W plus WB all over L. So let's write that down. So we have WA all over L minus W plus WB all over what? All over L. So this is what we have. So from here we can factor out W. If we factor out W, we have W into what? A over L minus what? 1 plus what? Plus B all over what? All over L. So this is what we have. So next we are going to be taking the LCM of that to get our value for shear force at point A. So let's continue with that. So we have shear force at A to be equals to what? We have W. Let me rewrite what we have there. We have W into what? A all over L minus what? Minus 1 plus what? B all over L. So if we take the LCM of this, is nothing but L. So this will be equals to W into what? Into L all over what? L divided by L is 1. 1 multiplied by A is A minus, this is A, minus what? Minus 1. So L multiplied by 1 is nothing but L. So we have plus what? L divided by L is 1. 1 multiplied by B is B. So this is what we have. So now from here, this is nothing but what? We can rearrange this to be equals to W into what? A plus B minus L all over what? All over L. So we know that A plus B is nothing but L, which is the total length. So we are going to replace A plus B with L. So this will be equal to W into what? L minus L all over what? All over L. L minus L is nothing but 0. 0 divided by L is 0, and 0 multiplied by W is 0. So our shear force at A is equals to 0. So this is what we have. So next, let's solve for the bending moment calculation. We calculate our bending moment values. Let's draw the shear force diagram. So I'm going to be representing, I'm going to be drawing down my dotted line. From every point there is a force or load. So this is what we have. From this point too, is what we have. So I'll draw my reference line for the shear force. So this is what we have. So I've just drawn my line. This is my reference line for my shear force. Anything above is positive, anything below it is negative. This is my reference line for bending moment diagram. So now let's draw the shear force diagram. Now at B, we have our shear force to be what? WA all over L, which is positive. So we are going to be tracing it. Let's take this point here to be our WA all over L. So we can say WA all over L. So of course, like I said before, going upward is positive and downward is negative. So from this point here, even up to this point, there is no load. So we can represent that with a constant line. So this is what we have. This is what we have. So what do we have next? We have our shear force at C. Our shear force at C is nothing but minus WB all over L. So we are going downwards towards the towards the negative direction. So this is what we have. So I can take this point to be minus WB all over L. Now similarly, there is no load in between this point, so we represent that with a constant line. And then finally, our shear force at A is nothing but what? 0. So we are going back to 0. So this is what we have. So this point, this part of course is positive, and this part is negative. So we can just shade it. This is our negative part, and this is what? This is our positive part. I hope you get that. So next we are going to be what? Doing what? The bending moment calculation before we draw the diagram. So keep watching. We are going to be solving for what? The bending moment calculation. So we have what? Bending moment calculation. So this is what we have. So for this beam we have here is of course a simply supported beam, and we know that for a simply supported beam, the bending moment at both points B, that is the bending moment at the two support, will be what? Will be equal to 0. So our bending moment at point A is equal to 0. Similarly, our bending moment at point B is equal to 0. So now we are going to be looking for our bending moment at point C. Now, bending moment we know is nothing but what? Force times perpendicular distance. So if we are looking for bending moment at point C, it will be nothing but what? The force here, which is WA all over L, multiplied by the distance, which is what? Which is B. So our bending moment at C will be equals to WA all over L multiplied by B. But of course, we are going to be considering upward force to be positive. We are going to be taking upward force as positive, and what? And downward force as negative. So of course, you know, this is WA all over L multiplied by B. So this is equal to WAB all over L. So that's what we have. So that will be all for our bending moment. So let's go over and plot this on our bending moment diagram. Now, before we proceed, like we have been doing in our previous video, you know that for every straight line on the shear force diagram, it will be represented with an inclined line on the bending moment diagram. So our bending moment at B is nothing but 0. So this is our point here at 0. Our bending moment at C is nothing but what? WAB all over L, which is positive. So we are going to be going upward, which is positive. Let's take this point to be our WAB all over L. So we have WAB all over L here. So this is what we have. So of course our bending moment at A is nothing but 0, so we are going backward to 0. So this is what we have. So of course this is positive. So this is what we have. So this is how to calculate the bending moment and shear force for a simply supported beam that has a concentrated load not at midspan. So that's what we have there. So you can also check, we have solved numerous numericals under this case, so you can go through for proper comprehension. So thank you for watching and have a nice day.